Greetings, everyone. Thank you for being part of Lattice Semiconductor's dynamic live panel discussion. I'm Jim Tavakoli, leading the Aerospace and Defense Division at Lattice, and I'm thrilled to guide today's engaging conversation today. Over the years and through several interactions with developers of next generation systems, I've had the privilege of witnessing groundbreaking innovations and advancement in this field. Space and technologies to develop next generation services impact our daily lives more than we realize. This panel discussion provides a platform for experts to share insights, exchange ideas, learn from each other's experiences, and collectively drive progress with all of you. Please join me in welcoming our esteemed panelists, Khalid Khan from Synopsys and Melanie Berg from Space R Cubed. Khalid and Melanie, welcome. I'll hand it over to Melanie to start the introduction, and then we'll dive right in.
Hello, everyone. I'm Melanie Berg, and I'm the CEO and founder of Space R Cubed. I have over 36 years of experience as a designer and verification ASIC and FPGA designer. In the past, I've had the privilege to contribute FPGA design for a variety of NASA missions, such as New Horizons, Pluto and Beyond, JWST, and Kepler. In addition, as a past member of the NASA Radiation Effects and Analysis Group, I've been able to contribute towards the radiation assurance of most of the NASA Goddard missions that I've flown. I am now focused towards research and development for mitigation strategies meant to protect against radiation or adversarial induced system malfunction. This includes and perhaps requires modernizing our test and analysis methods and insurance. I'm looking forward to our discussion, and thank you, Jim, for inviting me to participate in this panel.
Hello, everyone. I'm Khalid Khan. I'm a Director of Application Engineering for FPGA synthesis and prototyping products at Synopsys. I'm based out of Synopsys headquarters in Sunnyvale, California. For 20 years, I have worked on various FPGA synthesis, prototyping, and debug technologies. I started out as a space system engineer at the Canadian Space Agency. Then I moved out to Silicon Valley in California. I started at Synopsys. In my current role at Synopsys, I'm a product application lead engineer for FPGA synthesis and prototyping technologies. And I'm looking forward to today's discussion.
We're excited to have you both, so let's dive right in. Space exploration has always captivated humanity's imagination, from the early days of gazing at the stars to landing on the moon and beyond. Our fascination with the cosmos continues to drive innovation and technological advancements. Today, as we stand on the cusp of a new era in space exploration, communication, and utilization, driven not just by governments, but also by private entities, it's crucial to understand the latest trends, new services, and mission-critical platform requirements that are shaping this domain and their implications on the need for FPGAs, design tools, as well as test and verification methodologies. This leads us to the first question of our panel discussion today. Khalid, let me start with you. What are the major emerging technologies that are critical to making space exploration and operations more reliable and affordable?
Jim, we're living in extremely exciting times for the space industry. We're seeing a drastic increase in number of public and private sector space projects, from making humanity a multiplanetary species to building colonies on the moon, low orbit satellites to provide better services here on Earth, and finally, space tourism is becoming a reality. According to World Economic Forum, space economy is expected to reach $1.8 trillion by 2035. And space-based tourism alone is expected to grow $4 to $6 billion by 2035. So what does that all mean for microelectronics and FPGA market? As you know, FPGAs, or field programming gate arrays, are essential components in space-bound technologies such as satellites. FPGAs are relatively cheaper and provide great advantages in implementing custom logic and ability to reprogram and update logic when necessary. This makes FPGAs an asset for long-term space programs. For spacebound systems, FPGAs helps control many essential components from communication, sensor, instrumentation, data processing, and power management systems. On Earth, we depend on these satellite systems for day-to-day essential services, such as communication, weather, for our navigation system, for our radio, TV, and internet services. It is paramount for us to make advancements in spacebound technologies that are more power efficient, safer, reliable, affordable, and reusable. Lattice provides FPGA technologies through devices such as Avant, Certus NX, and Certus Pro NX. And Synopsys Simplify FPGA Synthesis tool provides or enables FPGA designers to develop highly safer and reliable designs for harsh space environments. Speaking of harsh space environments, I know you guys have been doing some radiation testing on Lattice FPGA devices. I have a few questions regarding the radiation testing. So, Melanie, in your experience, how the test mechanism have changed over the years, and what are customers asking for, and what is in pipeline for future development in radiation testing?
Well, colleague, radiation test and analysis for FPGAs is a complex field. The ultimate goal is to characterize a device's susceptibilities to radiation and requires in-depth knowledge for developing embedded test structures and their test systems or equipment. So just before I get started and fully into this, I want to make sure that we're on the same page with terminology. When I talk about embedded structures, as for instance, it's usually basic elements such as library components that are embedded within the FPGA or its IP cores. We're also talking about the inclusion of actual user applications that would be in flight for missions. Prior to testing, we download these test structures into the FPGA. When I talk about test structures, these are the systems that we use to actually drive the device under test, or I should say DUT, with its particular applications. And when we're talking about driving, we're talking about being able to apply stimuli, and we're also talking about being able to monitor the DUT's responses as it's being exposed to radiation. Now, when I entered the radiation community or the field in 2004, it was mostly government driven, and there was really little to no activity from the commercial world. The embedded test structures are extremely simple. We're talking about shift registers or transistor level investigation. And the test systems were also simple in their structures. And very limited on data capture. So how did we get away with all of this? Well, at the time, our systems, our space systems, were being created or developed using rad-hard FPGAs. Very, very expensive devices that are meant to fly with an extremely low probability for upset in space. So radiation data was pretty much inconsequential. It was more so a go, no-go, making sure that the device isn't going to cause anything destructive. However, today, commercial space and now government are looking for lower costs and much more performance, and COTS is that solution. However, or unfortunately, I should say, the downside of using COTS is that these components are magnitudes more susceptible to radiation than their radiation hardened counterparts. And because of their increased sensitivities, COTS forces us to not only add mitigation to protect against radiation faults, but also to perform much more in-depth radiation tests and analyses. So that means that our test structures have to mimic our in-flight applications. But guess what? This pushes our test systems to be much more complex in nature. And in turn, that complexity is becoming an extreme challenge for many of our test groups. However, at the same time, we know it's a need. So our customers are more and more, they are asking or demanding for a test as you fly type of radiation test. They really want to analyze the efficacy of their scheme or their design when it's exposed to radiation. And this is clearly something our old school methodologies cannot handle. So in response, SpaceRQ is leading the way for rad test and analysis, and develop systems to test systems. SpaceRQ has developed a compact, portable test system that can go to any kind of radiation test facility, and actually use that DUT or implement that DUT as if it would be operating in flight, i.e., a true test as you fly experiment. And as a matter of fact, we just completed a test campaign in collaboration with Lattice and Synopsys to study mitigation efficacy in Lattice Certus Pro and the Lattice Savant FPGA products. And the test results were great, and we're looking forward to do a lot more testing in the future. So
Fantastic. Thank you both for those insights. What I'm hearing is, undoubtedly, Khaled, as you mentioned, space market is a huge market and fast evolving. And Melanie, as you stated, I couldn't agree with you more. These systems are becoming much more complex, and system level holistic approach is needed. This leads me to wonder, as these technology advancements continue to emerge, how are the design and test methodologies of next generation space applications impacted? For example, today, to speed up the pace of innovation, space systems are being developed much faster. And flight test of prototype systems is now becoming part of the design, test, and verification cycle. This was not always the case. Today, developers have introduced flight tests as part of the entire development cycle, and within a matter of months, they can have flight test data that identifies reliability and robustness of the design based on real flight test data. This helps them implement and optimize how to best achieve their target reliability and robustness of the design. Developers can now evaluate also the robustness and efficacy of features such as triple modular redundancy, automatic error detection and correction, in-orbit reconfiguration, and always-on availability and operation of all of the systems in their next-generation satellites. Melanie, what do you think about that?
So, Jim, from my experience, what I can see right now, that missions are looking to heavily increase their autonomy in space, and you hit a lot of it. We're talking about artificial intelligence, high-speed data communication handling, and self-correcting architectures. But I really like that you touched on the point that we are also looking for speed of development cycles. With that comes a lot of IP core usage. Those IP cores are huge, complex black boxes, and that adds a significant amount of risk to our systems. In addition, they're also very difficult to mitigate. So this really increases the complexity and risk of our systems in general. We're talking speed, or trying to manage and trade speed, area, power, and cost. This truly increases the complexity of our systems. We're talking trying to balance speed, area, power, and cost. And because of the codependencies and their limitations of all of these items, smart trades have to be done as a part of system development. For example, due to power concerns, perhaps computational speeds have to be decreased, or because of area, perhaps we can only partially mitigate our systems. So for any system, the decisions made for its development have to go through an extreme assurance cycle. Or I should say, just as much concern for development or design has to also be made towards assurance. Um, and as I previously mentioned, tested fly is pretty much the only approach to guarantee that the final version of an application is reliable. However, we need to step back for a second, because before we even go to test as you fly, how do we know what to select or what to put into our designs? How do we know what are the optimal approaches? So if we look at mitigation as an example, right? Each FPGA type has its own sensitivities, right? And because of that, they require very customized mitigation strategies. So per FPGA type, we have to know which button to push on synopsis as to which mitigation we want. How do we know that? Well, we do a first look type of test campaign, very similar to what we have done with Lattice, as far as trying to figure out on the Certus Pro, which is an FD SOI type of technology, SRAM-based FPGA versus the Avant Lattice, which is a 16 nanometer SRAM-based FPGA. What are their susceptibilities and what kind of mitigation strategies will really work? Each of them, we wanted to be able to test their embedded scrubber systems. Are they working as expected? And again, do we use localized TMR? Do we use distributed TMR? Do we use block TMR? Will any of them or all of them work for us? And so we do have that first look data available, and that helps the users to be able to figure out, yes, that's the strategy that will fit into my FPGA, into my system regarding power and cost concerns, and are able to move on to, after selection, being able to actually do a system development and then a true test as you fly. So after all that's been said, Khalid, what do you think about all of that?
Thank you, Melanie. So, over the last 20 years, we have seen tremendous advancements and improvements in FPGA device technologies as well as software flows. These include FPGA device capacity, performance, power efficiency, and with the help of simplified synthesis tool, we added additional features such as safety and high reliability, runtime improvements with max parallel jobs, placement aware advanced synthesis engine for better timing QR and area congestion mitigation features. Synopsys also provides many other tools, services, and solutions to help detect design issues early in the design development cycle. These include tools such as Spyglass for HDL lint and clock domain crossing and reset domain crossing checks, VCS for simulation, Zoix for fault simulation, Euclid IDE for early RTL code development with auto completion of LRM compliant HDL code, ZeBu and HAPS for larger hardware assisted emulation and prototyping solution for billion plus gate systems, verification IPs and prepackaged verified RTL IPs from Designware IP component libraries, Verdi as a debug solution with hardware to RTL data signal mapping, expansion, correlation, and waveform comparison, just to name a few. In addition to that, Simplify FPGA synthesis tool, we provide several layers of high reliability features with synthesis output netlist, which include auto insertion of Hamming 3 encoding for FSM logic, triplication and duplication of design modules with block level TMR, distributed TMR, and local register level TMR, and for memory blocks mapping to ECC capable BRAMs, error flag insertion for error reporting on high reliability logic, and hardware level fault injection to functionally verify that your high reliability logic is implemented correctly in the FPGA.
Thanks for that, Khalid and Melanie. We've talked about reliability, that the importance of the robustness of these systems as they get more complicated. We've also briefly touched up on the importance of functional safety and how it enables a maximum uptime. But I wanted to ask Melanie, what solutions and strategies are developers employing to enhance the security of next generation space systems?
So, Jim, security has been a hot topic for me lately. I've been spending a lot of time actually trying to do research to advance the field of security and FPGA insertion in critical applications. Again, before I get started, and let's talk about terminology that's commonly used. When we talk about security in a government system, we're talking about CIA, which is confidentiality, integrity, and availability. The confidentiality refers to the potential of knowledge being leaked or theft of any parts of your system. Integrity is about your operation or your function doing what it's supposed to do when it's supposed to do it. Availability refers to a system and accessibility. Is it accessible when it's supposed to be accessible? Is it responding when it's supposed to respond? All of this adds another layer of complexity for mitigation or protection. What I didn't get to talk about in the last section, and I think this is probably a better place to talk about, is how do you assure these levels of complexity? Space Art Cube has developed a very complex system that tests systems, but it is able to mimic or emulate any type of peripheral that will go around an FPGA that would be in a space vehicle or even in an automobile or any other type of vehicle. And what that enables us is to create an assurance environment that can make sure that DUT is operating as it would in any real application. And that way, our data that we are collecting or retrieving is very reliable and will be able to give us great extrapolation of a characterization or potential risk analysis for the device that we're testing. And again, that includes not just radiation, but it includes reliability testing, and it also includes assurance for trust and security, being able to mimic an adversary that would try to be able to break into your system. So we are able to handle all of that level of assurance, which is a necessity to, again, the complexity, especially when we are trying to assure that a critical application is adhering to the requirements that were set forth to it. We are definitely leading the modernization to all of this type of radiation harness assurance and security assurance, and look forward to doing more testing with Lattice and Synopsys in the future. So thank you.
So just to add to that, Jim, functional safety and high reliability and security are critical to any infrastructure application, from transportation, industrial, and of course, even more so for space-bound systems. As systems in space environment are not easily accessible for replacing or upgrading parts. Hence, everything needs to have a minimum redundancy to avoid any catastrophic system failures, which could result in disruption of essential services, as well as financial losses in billions of dollars. To address this need, a simplified synthesis tool provides multiple high reliability automated mitigation techniques. For example, a single event upside error can occur when an ionizing solar particle strikes a sensitive design node, which causes the change in functionality of the FPGA design. To mitigate such errors, we provide several single-bit autocorrection and double-bit auto detection techniques with simplified high reliability features, which includes TMR, Hamming tree for FSM, ECC BRAMs for memories, error flag insertion for error reports, and for security, we provide RTL to bit file level encryption flow using the IEEE 1735 encryption standard. And we also provide Synopsys custom encryption methodology for RTL IPs. In addition, Simplify provides hardware-level fault injection for essential output netlist to functionality verify the operation of reliability logic implemented on the FPGA hardware.
Thank you for that, Khaled and Melanie. You know, the way I see it is as satellite networks grow in scale and deliver communication applications and services, a massive amount of user data will be transporting through these networks. As a result, not just reliability of these systems, but security and functional safety of these systems are just as important. We want to see not just secure bit streams through these networks, but also secure data streams are expected of both radio and optical networks in space. Let me now hand it over to Melanie for her closing comments.
Well, as you said, the complexity in space is real, not only on the development/design side, but also on the insurance side. And a lot of it has to do with the fact that, COTS are becoming our main go-to as far as device selection. Um, so SpaceR Cubed is now leading the way for studying mitigation efficacy and radiation harness assurance, including with security assurance for these complex systems. We're steadily collaborating with government agencies and with commercial aerospace to not only keep up with new technologies, but to find optimal methods customized for reliable critical applications. So thank you so much for inviting me to participate in this interesting discussion. As you know, it's a passion of mine. I can speak forever on it. And I do look forward to our future work together. Those who are interested in SpaceR Cubed, the information can be found on LinkedIn and also on our website, SpaceRCubed, that's CUBED, spelled out.com, SpaceR Cubed. Thank you, Jim.
Khaled, over to you for your closing comments.
Thank you, Jim and Melanie. It was a great discussion. As you know, safety and high reliability are paramount to any FPGA design. Synopsys provides many solutions for space, automotive, industrial, medical, and defense industries. We have many customers who use simplified high reliability mitigation features as a mandatory part of their safety requirement. A target FPGA device include large off-the-shelf FPGAs, as well as military grade, as well as the latest Lattice lower power FPGA devices such as Avant, Certus NX, and Certus Pro NX. We look forward in collaborating with Lattice as well as other aerospace automotive industry partners in helping implement the best-in-class high reliability and safety solution. Thank you for your time, and we look forward to your feedback and further collaboration in the near future. For more information, please visit us at synopsys.com. For any questions, please feel free to reach out to me. Thank you.
Yeah, thank you for that, Khaled. And let me summarize. The fast-growing space service industry is driving innovation in space systems and FPGAs. New requirements for miniaturization, low-power operation, and in-orbit reconfigurability are shaping the future of this critical technology. Advanced tools to increase robustness and sophisticated methodologies to test and verify functionality and reliability are shaping next-generation space applications. In closing, I want to thank you all for sharing insights on the dynamic landscape of the space industry and the indispensable role of groundbreaking technology solutions that enable the demand for various mission-critical requirements and application developments. Melanie and Khaled, thank you. At Lattice, we are all excited how our solutions, as well as that of our ecosystem partners, are continuing to enable innovation and for the designers that have rigorous requirements for next generations. For those who would like to learn more about Lattice products and solutions, visit our website shown on the screen. As well, to stay up to date with our latest news, be sure to follow Lattice on LinkedIn, Facebook, and Twitter. As well as Melanie and Khaled mentioned the respective ways for them to be connected out to you. Thank you.